When you've completed this lesson, you should be able to multiply and divide numbers that contain units and obtain answers that correctly express those numbers and units. You'll be able to express numerical values and units in prefix notation, such as 3.4 millimeters. You'll be given an equation with several terms, but you'll be able to check those dimensions for each item and then check the equation as a whole. And you'll be able to convert a physical quantity expressed in one set of units to an equivalent quantity in a different set of units. Photonics technicians are required to work with measurements that come in many different units, sometimes English, sometimes metric. They frequently need to convert between different systems of measurement. For example, the speed of light may be given in 186,000 miles per second or 3 times 10 to the 8 meters per second. Or you may encounter wavelengths of 0.55 micrometers or nanometers or angstroms. Let's look at an example problem such as the heat transfer rate in a laser. Delta Q over delta T equals delta M over delta T times C times delta T, where delta Q over delta T is the heat transfer rate, delta M over delta T is the coolant flow rate, C is the specific heat of coolant, delta T is the temperature change of the coolant, and you're measuring the temperature change of 17.7 degrees C with a flow rate of 33.3 grams per second, and the coolant specific heat is 1 calorie per gram degree C. What value in units are you going to record for the heat transfer rate for this laser? Wow, those are lots of units going by there. Well, we're going to return to that problem later on after we develop some skills on how to handle all of those different units. Measurements that you take should always include a value and a unit of measure. For example, 10 feet should always be recorded with both the 10 and the feet. 20 miles per hour, or 3 centimeters cubed, or cubic centimeters. Never just record the number without the unit of measure. Always record both the value and the unit of measure. When measurements are multiplied or divided, we handle the values and the units separately, but we handle them both. For example, if we multiply 10 feet times 20 feet, then we'll multiply the values 10 and 20, and we'll multiply the feet to end up with a result of 200 feet squared. If we multiply 20 miles per hour times 10 hours, we multiply the values 20 and 10 and the units miles per hour times hours. You'll notice that the hours in the denominator and the numerator will cancel, leaving us with just 200 miles. If we divide 5 grams divided by 10 centimeters squared, then we divide the values 5 and 10 and the units grams and centimeters squared to end up with 0.5 grams per centimeter squared. 5 pounds per cubic foot times 2 feet. We separate out the values and the units. 5 times 2 is 10, and we have the units. We have pounds per foot cubed. We separate out the foot times foot times foot, and the foot in the numerator and one of the foot in the denominators will cancel, leaving us with pounds per foot squared as the units that are remained. Now, many units will use prefixes for powers of 10, such as kilo. You're familiar with like kilometers. Well, here's a table of the more common prefixes that you'll encounter. You've probably heard of gigahertz and megahertz for 10 to the 6th. 10 to the 3 is kilo, as in kilowatts or kilometers or kilohertz. 10 to the minus 2 is familiar for centi, as in centimeters. 10 to the minus 3 for milli, as in milliwatts or millimeters. 10 to the minus 6 for the micrometers. And 10 to the minus 9 for or nanometers that you'll encounter a lot as a photonics technician. Now, the units of measure must be included in all your calculations in order to yield the correct units for your answer. So it's important that we continue to use all the units. So let's look at a common physics formula, such as distance is equal to the velocity times the time plus 1/2 the acceleration times the time squared. Here are the units for the metric system, for example. So for metric values, let's just look at the units, how those units would work out. If we multiply a speed in meters per second times a time in seconds plus 1/2 times an acceleration in meters per second squared times a second of time squared, you'll notice that the seconds here will cancel, leaving us with just meters. And here we'll have second squared divided by second squared will cancel, leaving us with just meters. So the distance results in meters, which is what we'd like to see, a distance in meters. What if the values for all of our speeds and accelerations and so on were in English system, as in miles per hour and miles per hour squared in hours? Well, we would hope then that the distance would result in a distance calculation of miles. The correct types of units are important. Distance, speed, area, and temperature, and so on. We don't want to mix those up. And the correct scale of the units are important too. We don't want to mix them up. Meters, feet, miles, and inches they're all distance units, but we don't want to mix them into the same thing, so we convert them. For example, if we're going to be adding distances of 1 feet plus 6 inches, well, we want to convert them all to the same unit of measure. So we'll convert 1 feet to inches, which would be 12 inches, so that 12 inches plus 6 inches would be 18 inches. You probably would have done that anyway, but we want to be sure to do that in a more complicated problem too. And some conversions aren't so easy, and for that we need to use what's called a unit ratio. So let's learn about unit ratios and how that will help us mix up the units in calculations. A unit ratio is really just a fraction. Don't get scared by the word fraction here. It's a fraction that's formed by two equivalent quantities. For example, 100 centimeters is the same as 1 meter. So if we put those as a form of fraction with 100 centimeters over 1 meter, that's really just equal to 1. Or we could put 1 meter over 100 centimeters. That's also a unit ratio. It's also equal to 1. We could also have 1 foot over 12 inches. That would also be equal to 1. Or 12 inches over 1 foot. That would be equal to 1. And multiplying by 1 is just, it results in the same number, just changes some of the units around. So when we multiply by a unit ratio, such as 6 feet times multiplying by a unit ratio of 12 inches over 1 foot, we multiply the values, we pull out 6 times 12 over 1, and we separate out the units, which would be feet times inches over feet. And you'll notice that the value, 6 times 12, would be 72, and the feet will cancel in the units portion, and all we're left with is inches. So the resulting answer is 72 inches. So look at the big picture now. 6 feet times a unit ratio, which is equal to 1. 6 feet times 1 equals 72 inches. So 6 feet equals 72 inches. So we've converted 6 feet into inches. So in general, we can convert a measurement, say a measurement A, in some given units to a different unit by multiplying by a conveniently chosen unit ratio. Now, how do we choose that unit ratio? The unit ratio is, the numerator will be the desired unit we are trying to achieve, and the denominator will be the given unit that we started with. So we start with a number and the unit before the conversion, multiply it by a unit ratio that we form, and the result will be the value and the desired units. Let's see how that works in an example. Suppose we have a distance of 10 miles and we want to find the same distance in feet. From the table we find that 1 mile is equal to 5,280 feet. So we can form a unit ratio with that relationship. Now we can form a unit ratio of either 1 mile over 5,280 feet or 5,280 feet divided by 1 mile. Which one would be the right one to pick? Well, since our given unit is miles and the desired unit is feet, then we'll use the second unit ratio because we want the desired unit to be the numerator. Remember that expression? The desired unit will be in the numerator. So the given unit is 10 miles and the desired unit is 5,280 feet divided by 1 mile. So here's our unit ratio. And so then we have our values. We pull out the values out of our multiplication. 10 times 5,280 all divided by 1. And we pull out our units. Miles times feet divided by miles. And you'll notice that the miles will cancel just as we wanted them to, leaving us with just feet. And the resulting answer is 52,800 feet. Here's another example. Suppose we have a distance of that 52,800 feet and we'd like to find the same distance in inches. Well, this is just another application of a unit ratio. From the table of conversion factors, we can see that 1 foot equals 12 inches. And again, we can form one of two unit ratios, either 1 foot over 12 inches or 12 inches over 1 foot. Which one should we pick? Well, our given unit is feet, 52,800 feet, and the desired one is inches, and so we will pick the second one again, just like before, 12 inches in the numerator. So our given number is 52,800 feet. Our unit ratio is 12 inches over 1 foot. Our values, 52,800 times 12 over 1. Our units, feet times inches over feet, where the feet cancel. And our resulting value then is 633,600 inches. And so we have that a distance of 52,800 feet is equivalent to 633,600 inches. Well, we can combine two conversions because all we're doing is multiplying factors. We can multiply two factors. So suppose we start with that given distance of 10 miles and we're asked to find that same distance in inches. So we're combining the previous two examples into one. From the table we have our previous two relationships. The 1 mile is equal to 5,280 feet and 1 foot is equal to 12 inches. So we can form two unit ratios now. We'll multiply by both unit ratios so that we can cancel the given units, leaving the desired units. I expect that you can see the pattern that we're beginning to develop here. We'll pick the unit ratios that will end up with canceling the units. Now this one is a little bit more complicated, but you'll notice that we want the miles to cancel first of all. So we'll pick our unit ratio 5,280 feet over 1 mile, right? But now we have feet and we're trying to get to inches, and so we're going to now multiply by 12 inches over 1 foot, and the feet will cancel. And so the result is that we'll have all these values to multiply together. 10 times 5,280 times 12 divided by 1 times 1. And we'll have all these units to multiply together, and most of them will all cancel out except for the one that we're left with, the desired unit. And the result will be the same result we had before, 633,600 inches. But you see how that we did that all in one big, long calculation. So now I think we're ready to work on that opening scenario problem where we had to deal with lots of different units together. Let's look at that equation again. we can substitute in the given values and work with those units. So we substitute in 33.3 grams per second for the delta M over delta T, the C value of 1 calorie per gram degree C, and a delta T of 17.7 degrees C. And we pull out all the values, 33.3 times 1 times 17.7, and pull out all the units and see how we cancel the units out. And you see what we're going to be left with? We're going to be left with calories per second, which is a heat flow rate, which agrees with what our formula should give us. And the result is 589.4 calories per second. So now let's look at some of the practice exercises that are in the back of this module. Again, as before, we'll not work every single one of the practice exercises, but just a few of them to give you a sense of confidence that you can work the rest of them by yourself. First thing we're asked to do is multiply and divide some quantities and obtain the correct number in units. So if we multiply 5 pounds times 10 feet, as you have seen in the text, we're going to multiply the values and the units separately. So multiply 5 times 10 and pounds times feet to end up with 50 pounds times feet, or more commonly shown in the physics books as foot-pounds. A second problem would be 100 newtons divided by 5 meters squared, which we could write as a fraction of 100 newtons divided by 5 meters squared. We will pull the values out, pull the units out, and evaluate the values and evaluate the units. Here's a third example, 16 miles per hour times 0.5 hours. So we'll pull the values out, 16 times 0.5, pull the units out. In this case, the units, part of them will cancel, and the result will be 16 times 0.5 is 8, and the units that remain are the miles. Here's another example, a little more complicated, 62.4 pounds per cubic foot times 10 feet. Again, we pull the values out and the units out. We'll express the cubic feet as feet times feet times feet, so that one of the pairs of the feet will cancel, leaving us with just pounds divided by feet times feet, better known as pounds per foot squared, and the value will be 624 pounds per foot squared. Exercise 2 asks us to complete the table of factors, prefixes, and symbols for the measurement units. And you should be able to do this based on the table that's in the text. Now exercise 3 asks you to change the power of 10 notation to a prefix that's applied to the unit. So if your result came out to be 5.6 times 10 to the third meters, what prefix would you put on that? Well, that would be the same thing as 5.6 kilometers, or kilometers as we're used to saying. And the abbreviation for that would be km if you wanted to use the abbreviation. 6.8 times 10 to the 3 calories would also be 6.8 kilocalories. 10 times 10 to the minus 2 meters would be 10 centimeters, using that table that you just completed in the previous exercise. 5 times 10 to the minus 3 meters. What prefix would be appropriate for 10 to the minus 3? That would be millimeters. 3.14 times 10 to the minus 9 seconds. The prefix for 10 to the minus 9 would be nanoseconds. Table 3 then, we could be used to replace the power of 10 multipliers with actual values, with prefixes. So that if we had 10 to the minus 3 meters, we could use millimeters. 10 to the minus 3 grams would be milligrams. 10 to the minus 6 calories would be microcalories. 10 to the minus 2 meters would be centimeters. Exercise 5 asks you to rewrite 15,600 grams using power of 10 notation and kilograms. So we have to determine what multiplier could we pull out of the 15,600 to use a power of 10 notation. And you can see that you could divide 15,600 by 1,000 or by 10 to the 3, which is the same as a kilo. And so you'd end up with 10 to the 3 grams or kilograms for exercise 5. Exercise 6 is a good practice in verifying how the units work out in an equation. And this asks you to do this for both English and SI units for the equation where the velocity is equal to the initial velocity plus the acceleration times time, a good physics equation that you may have encountered in one of your physics courses, where VF and VI are the final initial speeds in feet per second or meters per second, and A is the acceleration in feet per second squared or meters per second squared, and T is in time, in seconds. So in English, the way that would work is you would substitute in those units for V, feet per second, and acceleration is feet per second squared, and time is in seconds. And you can see that as you expand out the second squared, that one of those seconds will cancel, and you'll end up with feet per second plus feet per second, which of course is a feet per second value. And so you'll have feet per seconds on the left side of the formula, equal sign, and feet per second on the right side of the equal sign, which is a good result. In the metric system, a very similar result. You'll have meters per second squared in seconds, and the seconds, one of the seconds will cancel, leaving us with meters per second plus meters per second on the right side, such that meters per second equals meters per second, and so everything checks out very nicely, and the formula is consistent with the units of speed. Exercise 7 asks you to verify the units work out correctly for a little bit more complex equation, where we have the electrical resistance is equal to the electrical resistivity in ohms centimeters times the wire length in centimeters divided by the area in centimeters squared. And if you substitute in those units, you'll have centimeters canceling in the numerators and the denominators, and the result will be ohms equals ohms, which is again the units will be consistent for that formula. Exercise 8 asks you to convert 150 centimeters to millimeters. Now you'll note that 1 centimeter equals 10 millimeters, and so we'll use that as a unit ratio. We'll multiply 150 centimeters times 10 millimeters over 1 centimeter, where the desired unit is millimeters on the top, right? So we'll group the values together and the units together, and the centimeter units will cancel, leaving us with just millimeters, and the result will be 1,500 millimeters. Exercise 9 asks you to convert 21 liters to gallons. Again, we'll form a unit ratio using 1 gallon to equal 3.785 liters, and we'll have to multiply by a unit ratio. Again, we'll put the desired unit on top, and that will group us the values of 21 divided by 3.785, and the units will group together so that the liters will cancel, leaving us with just gallons, and those values will evaluate out to 5.5 gallons. Exercise 12 is a little bit more challenging. It asks you to convert 10.5 miles per hour to feet per second. This time we'll have to use 2 unit ratios to get there. But we'll use the relationship of 1 mile is equal to 5,280 feet, and 1 hour is equal to 3,600 seconds. Watch how this works. We start with 10.5 miles per hour, and we want the result of feet per second, so we want to get feet in the numerator. So feet will be the desired unit, and so we'll put that on the top such that miles will cancel. We'll see that coming, right? Miles will end up canceling, and we'll multiply by a second unit ratio of 1 hour over 3,600 seconds, so that seconds will end up in the denominator and the hours will cancel. You see how we're looking ahead? So we chose our unit ratio so that the units hours will cancel. Then we group all the values together, multiply 10.5 times 5,280 divided by 3,600. The result will be 15.4. And we group all the units together, and sure enough, the miles will cancel and the hours will cancel, leaving us with feet per second in our result. And our resulting answer then is 15.4 feet per second. Alright, and that concludes Module 2 for Mathematics for Photonics Education. I hope this gives you some confidence to do the rest of those practice exercises and feel ready to move on to the next module in this course. Good luck!